Hello everyone, I am Gurpreet Kaur, Assistant Professor in CSE and CA Department, School of Engineering and Technology, City University, Ludhiana. Today I am going to present the topic Computer Architecture. Firstly, we know what is architecture. Basically, it tells how the hardware components they are connected with each other. So this is the brief outline of my topic. First is Flynn's classification, parallel processing, then pipelining, data hazard, risk pipeline and array processor. So the very first topic is Flynn's classification. As it depends upon two factors, first is instruction stream, second one is data stream. So it is broadly divided into four categories, that is SISD, SIMD, MISD, MIMD. So first category is SISD, that is single instruction, single data stream. As its name clear, it executes single instruction at a time, and these are basically uniprocessors. Suppose we having one CU, that is control unit, which is further connected to processing unit PU and which is connected to the local memory, and these are basically the uniprocessors. Next category is SIMD, single instruction multiple data stream. As its name clear, it operates on single instruction but on multiple data streams, that is different data streams. In this suppose we having one control unit which is common to multiple PUs, that is processing unit, and we having multiple number of local memories, suppose M1, M2 and so on. And these are its best example is parallel computer. Next category is multiple instruction single data stream, that is MISD. As its name clear, it operates multiple instructions that are operated simultaneously on a computer system but on different data stream. Its best example is pipelining. Next category is MIMD. As its name suggests, it is multiple instruction, multiple data stream. It is also a multiprocessor machine which executes simultaneously multiple instructions but on multiple data streams. But practically in real life, it is difficult to create. Next we have the concept of parallel processing. Basically we need parallel processing in order to increase the performance of the system. Ultimately the throughput of the system increases. This can clearly visible with the help of this flowchart, this diagram. Firstly, the instructions they get fetched from the memory into the registers. Now we having adder subtractor, integer multiplier, logic unit, shift unit, incrementer, floating point add subtract, floating point multiply, floating point divide. For example, consider an example which involves addition, subtraction, multiplication and division. The instruction which involves addition, it goes to adder part, and which involves subtract, it goes to the subtractor part. And the instruction which needs increment, it goes to the incrementer. And so let's say suppose an instruction which include decimal value as an integer as well as it involves addition sign or multiplication sign, it will go to floating point multiply, or if it involves decimal value with integer with division sign, then it goes to floating point division. So we can see here that multiple instructions they are executed simultaneously, hence the performance of the system increases. Ultimately the throughput of the system increases. Next we have the concept of pipelining. Pipelining basically refers to a technique of decomposing the instructions into sub-instructions. For example, let's say suppose we having some value which we pass to A, which is stored in register R1. Another we pass the value B, which is stored in register R2. Then multiplication of both A and B, they are stored in another register, that is R3. And then we again pass some other value C, which is stored in register R4, and addition of R3 and R4 respectively, it is stored in register R5. It is well clearly shown in this figure in this flowchart. For example, we pass some value A, like suppose 3, which is passed to the register R1, and let's say suppose the value 2, which is passed to register B, which is stored in the register R2, and the value of both they get multiplied and stored in another register R3. Let's say suppose 4 into 3, that is 12. Again we pass another value C as 2, which is passed to the register R4, and addition of both, that is R3 and R4, addition of both, that is 12 plus 2, that is 14, which is stored in another register, that is R5. So we can see that multiple instructions, they are executed simultaneously. It saves our time, speed of the system also increases, hence throughput of the system also increases. Next we are having types of pipelining. First is arithmetic pipelining and second one is instruction pipelining. So in case of arithmetic pipelining, we having arithmetic problems which are divided into sub-problems. Let's say suppose, consider an example. For example, let's say suppose x equals to 4.3 into 10 raised to power 3. And consider another integer y equals to 0.23 into 10 raised to power suppose 2. So we have to firstly consider these four basic steps. Firstly, we have to compare the exponents, then align the matrices, then add or subtract the matrices, and last step is normalize the result. So these steps are very basic in every instruction, in every example. So these steps are to be followed. Firstly, we have to compare the exponent. Let's say suppose the example which I already told, 4.3 into 10 raised to power 3. And another one is 0.32 into 10 raised to power 2. So we have to compare the exponents, that is 3 and 2 will be compared. They are differ, so we make 2 as 3. And then second step is align the matrices. Now we have to align the matrices, and according to our instruction, we have to add them or subtract them according to our example. If it involves addition part, it gets add. If it involves subtraction, then it will get subtracted. And last step is to normalize the result. For example, the example as I already told, 4.32 and y equals to 0.32. They both get added and the rest part is exponent. We have to normalize them. We have to compare 3 and 2, and by making 2 as 3, by placing the value of the decimal to the left side of the integer. Hence the result get normalized. Next we having instruction pipeline. In instruction pipeline we having few steps, like firstly is we have to fetch the instruction from the memory, then decode the instruction, then calculate the effective address. The next step is to fetch the operand from the memory. The last step is to execute the instruction. So these are the steps, that is fetch the instruction from the memory, that is denoted by FI, decode the instruction denoted by DA, calculate the effective address, then fetch the operands from the memory, that is denoted by FFO, execute the instruction denoted by EX, and store the result into the memory, which is denoted by WB. So it's visible with this, so this diagram is visible. It can clear with this diagram. Firstly, we have to fetch the instruction from the memory, first step. Then second step is to decode the instruction from the memory. Then check whether there is a branching or not. If there is a branching, the next step is to handle the interrupt. If the interrupt occurs, then check whether there is a need to update the PC or not. PC is program counter, which hold the address of the next instruction to be executed. Then if there is a need to update PC, update it and empty the pipe. If there is no interrupt occurs, then it will pass the value back to the memory. Then move back to the branching step. Branching means it involves go to or jump statement. If there is such condition, then it will check. If there is no branching, it will come back to the next segment, that is third segment. It will fetch operand from the memory, then execute the instruction. Again it will check whether there is an interrupt or not. If there is an interrupt, it will follow the same steps as I discussed earlier. If there is no interrupt, then it will again write back the result back to the memory. So these are the stages in pipelining. So there are some stages, let's say 1, 2, 3 up to so on 13. and instruction branch again from 1, 2, 3 up to so on 7. So first step is fetching the instruction, next step is decode, then again fetch the operands, last step is execute. For stage 2, whether the previous instruction is decoding, this another instruction, new instruction is fetching the instruction from the memory. In previous stage, the instruction will get the operand from the memory, and in second instruction it will decode. In previous instruction it will execute the instruction, but in new one it is fetching operand from the memory. So there is a change in the state, but simultaneously instruction takes place. This is the concept of pipelining. But after third stage, we can see that there is some stall, there is some pause, which is termed as stall insertion, which I discussed later. Next concept is data hazard. Now what is data hazard? When there is a conflict occur between between instructions. Suppose we are storing some data into instruction and again we try to overwrite it, it will lead to conflict, that is data hazard. There are some types of data hazard in, like first is RAW, that is read after write, then WAR, write after read, last is WAW, write after write. First one is read after write, as it's also known as true dependency. It can best clear with the example. Let's say in instruction 1 we having the instruction like R5 and R3. Let's say suppose R5 having value 5 and R3 value having 3. They both get added and stored onto the register R2. Here the value of R5 and R3, they both get added and stored in R2. It is written into the R2. But in next instruction, again we are reading the value of R2 and again using the value of R2 as a reading mode and take R3 another register. So let's say suppose it takes value 3 and both get added and it will store the result onto the R4 register. Previously it is writing the result into the R2 register, but in the new instruction it will again reading the value of R2. So the conflicts occur after writing the instruction. So this is termed as read after write. Next we having write after read. It's also known as anti-dependency. Let's say we having example in first instruction like R4, which stores the resultant of R1 and R5 respectively. Let's say suppose 1 is stored in R1 and 5 is stored in R5. They both get added. Let's say suppose 1 plus 5 equals to 6, which gets stored in R4 register. Here we can write the value onto the R4. And in another instruction, we having R1 as a value 1 and R2 as value 2. They both get added and stored the result onto the R5. Previously we are reading the value of R5, let's say suppose 5, but in this case we are writing the value in another instruction. In new instruction we are writing the value of R5. Previously we read, now we write. So the conflict occurs, which is termed as write after read, because it occurs after reading the value of R5. Next is write after write, that is WAW. Consider another example, instruction. Let's say suppose R2 which stores the value of R4 and R7. Let's say suppose R4 having value 4 and R7 having value 7. They both get added and store the result onto the R2 register, or write the result onto the R2 register. 4 plus 7 is 11, which stored on the R2. Again we are taking the value of 1 as R1 and 3 as value of R3. They both get added, which comes 4, which is stored in the R2. In previous instruction we are writing the value onto the R2 register. Again we are writing the value in another instruction, we again writing the value onto the R2 register. So this conflicts occur after overwriting the value of R2. So this is termed as write after write. Now next is how to handle the data hazard. So it's very important to handle the data hazard. Let's say suppose we having code reordering. Code reordering is the best way to handle the data hazard. Another way is stall insertion, as I discussed earlier. We can pause the instruction by introducing the new instruction, that is NOP, that is no operation instruction. It does nothing but it provides delay to the instruction. By this way we can handle the data hazard. Next we having RISC pipeline. As we know, RISC stands for reduced instruction set computing. So it's a RISC pipeline which also follows the same stages as the simple pipeline. The stages like fetching the instruction from the memory, decoding the instruction, calculate the effective address, fetching the operand from the memory, executing the instruction, and last is write the result back to the memory. So the same steps to be followed in the RISC pipeline, but the difference is that in case of RISC pipeline, we can achieve CPI equals to 1. CPI term, that is cost per instruction, which is achieved to be 1. This is not happening in case of simple pipelining, so that's the basic difference between RISC pipeline and simple pipelining. Let's suppose consider an example in which we can say that instruction which is generally defined as n into m, that is number of processor into local memories. Let's suppose for first instruction it is I1 equals to N1 into M1. Let's suppose for second instruction it is I2 equals to N2 into M2. But in both the cases it takes CPI equals to 1. Similarly for 50th cycle it takes I5 equals to N50 into M50. It also consumes CPI equals to 1. Similarly for 100 instruction it also takes CPI equals to 1. So it is achieved only in case of RISC pipeline instead of simple pipeline. Next we have the concept of array processors. What are array processors? They are large group of data which perform simultaneously in order to increase the performance of the system, ultimately increase the throughput of the system. So these are of two types. First is attached array processor and second one is simmed array processor. Here we can say in attached array processor there is a general purpose computer which is further attached to input output interface. For peripheral devices it will get connected to input output interface. Next it is further attached to the attached array processor, further which is connected to local memory. Now the local memory and the main memory, they can communicate with each other using high speed bus. Next type is simmed array processor, that is single instruction multiple data. It follows the same structure as in case of simmed Flynn's classification. We having single control unit, that is a master control unit, which is common to processing elements, that is PE1, PE2 up to so on Pn respectively, and M1, M2 up to so on Mn, these are the local memories. So one common CU which is connected to PEs and local memories, which is further attached to the main memory. They can communicate with the main memory and store the result back to the memory. So the structure is similar to the simmed, which is the main category of the Flynn's classification. Its also aim is to increase the performance of the system by increasing the throughput of the system. And remember that each PE, it consists of ALU, that is arithmetic logic unit. Thanks.